welcome. Welcome, hopefully back, everybody, to our second webinar in our webinar series. We started last month with water analysis, and now we're continuing with an overview of pre-treatment options for the reverse osmosis. Today I have a new partner. So Christian Krumpholz from our sales team is with me. And since he's our most senior sales engineer, I will pass all the complicated questions to him.
Okay.
Let's see if he does another webinar with me.
Let's hope so, yes.
Okay. And yeah, René Scholz is helping us on the chat. If you have any questions, feel free to write. We hope you all enjoy the webinar, and we hope you don't hear so much wind because there's quite a storm here outside.
So let me say also some words about that.
Great.
So thank you very much, Birgit, for letting me in into this special webinar, kind of seminar for the World Wide Web here. I'm normally a face-to-face guy, and it's new for me, so sorry for that, but I will do my best. And I have brought with me, after this invitation, a little present, like a good guest do that.
Oh,
so,
okay.
And my present is a membrane.
Excellent.
Wow. And it's a bit of motivation why we are doing this webinar, because pre-treatment for RO means the RO is in the center of our thinking. So why do we ask for a good pre-treatment for RO? If you see this cross-section of the membranes, you see the narrow channels there, and the narrow channels have to be flown by the feed water. And the feed water, the better prepared the feed water is, the easier goes it through this narrow path through the membranes. And that's more or less the motivation of this webinar we are doing today.
Perfect.
So,
okay.
Let's start.
Great. Then we'll start right away with the agenda. We'll show you some basics of the pre-treatment, recap a bit the last webinar also, and then we will show three very important pre-treatment options, which are filtration, iron manganese removal, and softening. And we'll show you a few project examples as well.
So the basics of pre-treatment. Pre-treatment objective would be one of the parts we want to give you a presentation of. Which constituents cause problems? We had seen a lot of things on the previous webinars about that. The overview of technologies and which pre-treatment for which water, which is also very interesting for everybody of ours, just to see what is important.
Okay, so the objective basically, as Christian said before and showed you with this cross-section of the membrane, we want to protect the RO. Exactly.
Always remember.
And of course, the EDI from any substances that can damage the membrane. We want to avoid fouling and scaling. You see there are very small cross-sections, so they can easily get clogged up. Of course, in the end, this is to extend the service life of the membranes, because we don't want to exchange the membranes every second year, obviously. And we want to improve the RO operation point. Let's say you have a lot of scaling in there, you will have a higher pressure loss, obviously.
Yeah, yes.
So you will need more energy, or you will have some loss of permeate flow, right? So if you don't have the right pretreatment, or you have no pretreatment at all, that leads to performance reduction, higher energy consumption, frequent cleaning or replacement of the membrane, and in extreme cases, we all hope not to see that, total failure of the system.
Yeah.
But this is the worst case of what can happen. So let's say pretreatment is maybe not as interesting as reverse osmosis, but it's very, very important, actually.
Yeah, it's first step to have a really successful working RO. And if you see here, the first topic, protect the RO and EDI from the membrane damaging substances. The EDI is normally protected by the RO, because the RO makes permeate, which is really particle-free. But you have substances inside which are not really removed before. So if you think about an antiscalant
Right.
RO, then you have a rest of calcium, magnesium, so the hardness, and that could damage the EDI. So we have to think about the whole system, not only the single RO.
That's true. That's true.
Okay, which constituents cause problems? I think this is an answer from participants during our last webinars. And I think it's the spectrum of the typical verdicts. So calcium, iron, manganese is a often captured problem. Silica is also sometimes a problem in this EDI systems and also ROs. And it's one of the hardest things and problems we have to occur. CO2
Exactly.
is also, and the others, yes.
Okay, so we'll go for the most important ones. This is just to show you again the principle. So we have the pretreatment, in this case a softener, but could also be filtration stage, could be iron removal, whatever.
Yeah, yes, activated carbon, if
Exactly.
chlorine is a problem. There are a lot of playground in the pretreatments.
Exactly. And then we go for the reverse osmosis and the accessories.
Okay, the overview of technologies. So starting with the removing of TSS, so total suspended solids. I think there are in this region the sand filters, multimedia filters, activated carbon filters, filters with special materials, which we are explaining afterwards, and even ultrafiltration. And then it starts moving to the right side, and there it goes from the undissolved to the dissolved substances.
Right.
And there we have a removing of iron and manganese. And iron removal is a classic method, but it's not as easy as it seems. So we will see it afterwards. Manganese removal, even harder, more or less. An alternative could be an operation of the RO with antiscalant. It's only at low concentrations possible, and we have the problems that it's only shielded more or less, and it's not removed. So if you have an antiscalant, you not remove anything. You add some chemistry, and you have the iron and manganese in a form which doesn't cause problems if you are lucky. And the same is with the hardness. So it's more or less cause no longer problems in the RO, but in the following process, we have a certain amount of hardness, which could make our life not so easy. So removing of hardness will be the last point, and it's a softener normally, and we have some strategies to have a softening process.
Exactly. Okay, so which pretreatment do we choose? Most of our projects are with drinking water, with feed water. So usually we need some sort of softening because except for very, very soft drinking waters, usually you have enough hardness to damage the RO. It could be that you need to remove free chlorine if you have drinking water where chlorine is actually dosed. That could be done with activated carbon, dosing of sulfide. This is not such a complicated topic, so we won't discuss that in detail later. Well water, of course, you could have solids, for example, in karst areas. You might have seasonally some solids in the wastewater or in the well water, or generally you could have from the pumping and so on solids in there. Very often you have some sort of iron and manganese removal and also softening. And surface water, either from a sea, this is actually from the seaside, from a lake, from a river, you would always need a filtration. These are the complicated ones, let's say. If the water quality doesn't fluctuate too much, you could use a sand filter. For example, if you have water from a lake, from quite some depth. But in the case of a river, for example, you have a lot of fluctuation, and there actually an ultrafiltration, maybe with coagulation beforehand, flocculation, coagulation would be necessary. Sometimes iron and manganese are present, but I think they're mostly oxidized.
Yes,
so
yes. You have the surface water, you have access to oxygen, which is not happening in the well water, which comes from deep wells where no oxygen is anymore available.
Exactly. And remember, we said that in the last webinar, it's important to measure always iron and manganese in the reduced and the oxidized form, or let's say suspended and dissolved. So we'll start with the filtration.
Okay, when is filtration required? So I think we have to think about if the TSS, the total dissolved, total suspended solids, is very, very high. What is filtration? Filter assembly. We will have a few words about filter media, the filter series of Herco, our product program, and we say something about dimensioning of filtration stages.
Okay, then let's start right away. When do we need a filtration? So drinking water, we already labeled the different water sources, sort of.
Yeah. Yes.
The easy one, usually you don't need a filtration. You have some, the water supply company usually does that already. So you might want to have a fine filter, these small filters that we offer as well, which can be with backwash or without backwash. Possibly HSF sand filter. Those are also the small ones. We will introduce them in detail. But usually, if the water source, if you don't have doubts about the water source, let's say, I mean, in some countries it could be problematic. Like we have done projects in Mexico, and there the quality was not so good, maybe. But normally it shouldn't be a problem. So it would be.
I think in Mexico, sorry for interrupt you, but in Mexico, I think it's mostly the silica which is a problem, and then we can filter what we can, but we cannot filter it out. So
you're right, the silica is a lot more problematic than solids, actually. We had a few projects that were quite interesting. Yeah, that's because there's a lot of volcanic rocks there, like in some other countries, and we don't have that in Europe, fortunately, let's say. Okay, so you might need an activated carbon filter in the drinking water too, to remove free chlorine. We'll also remove organic matter and so on. Then if you have a well water, that's a lot more probable that you would need a filtration. And usually we would recommend MFT filters, right?
Yes,
Not the simple ones, but rather the MFT.
So in the surface water, we called it the expert level because it's sometimes not so easy, because the filtration normally is always required, because we have everything in the surface water, starting with little fishes and everything what is in the water. If rainwater comes, or if a heavy rain or a storm like today, then the surface water looks very different from a surface water in winter time when nothing happens. So filtration always is required. And ultrafiltration sometimes is necessary, because if the fluctuation of this rainy waters or something like that goes into turbidities, which are very, very high, then we have to think about the best strategy to filter it out. Precipitation or flocculation before the filtration may be needed. Also in the ultrafiltration, it works a lot better if you have microflux and flux before the ultrafiltration. But this will be not the topic for today, because this will bring us maybe in 2 hours, 3 hours, not to the end.
And it's not the most common case, so we'll try to focus on the common ones. But if you guys are interested in the more advanced ones, drop us a line and we'll do a webinar on that as well. Okay, what is filtration actually? When we're talking about filtration, in this case, we talk about depth filtration with granular material. So that could be sand, gravel, hydroanthracite, actually also carbon and so on. Also the media that are used for iron and manganese removal, that's also filtration. Only now we focus more on the removal of TSS, and then we'll come to iron manganese removal later. The filtration process always has an initial phase. That's the buildup of the filter cake, because the filtration actually works better once you have a filter cake. So once you have accumulated a few solids there, then you have the actual filtration phase where the quality is very good of your filtrate. And then you have either breakthrough, so you would wash out solids again, or actually we want to break off before that point, obviously. So when we see a pressure increase because we have a lot of filter cake, then we say, okay, this is the end of the filtration phase and we need to do a backwash.
Exactly. So sometimes it's done by experience. If you have a running filtration process, you can decide yourself when the differential pressure is critical and then make a backwash after this time, and the time sequence is normally every time the same.
Okay, good. Then let's...
So the typical filter assembly. So for these small filters in our product program, you see a vessel where the material is in, and we filter from the top to the bottom with this dirty water. And the control will be done by a control valve, central control valve on top of this vessel. That's the easy way. So the flow direction during operation from top to bottom. During backwashing, this will be countercurrent, so it will be going from bottom to top. Backwash is normally usually only timer controlled, and if necessary, you can have it pressure controlled, differential pressure controlled. But then you have to live with the situation that you have no water during the backwash. And it's better to have a timer controlled operation, because sometimes during the night you don't need any water, and then you can backwash the system.
I think it's more common to have the pressure controlled also for the MFTs, right?
Yeah.
For the larger systems.
Yes, for the larger systems, yes. So the filter bed is the coarse gravel layer for uniform hydraulic distribution. So filter gravel for actual filter effect. We have some freeboard for expansion of the filter bed during backwashing. So because you want to lift the bed during the backwash, just to break up this channels which have been built, and the material which has to be the dirt that has to go out of the system. The installation of the central pipe with these filter nozzles is a common used process, because we have to have a filter nozzle just not to wash out the filter material from the system during the operation.
Exactly. Okay, perfect. Then we come to filter media. So we have a lot of different media. Basically, you can divide up the media into two types, let's say. One is the mechanical ones, let's say. So they have a physical effect. The other ones are the chemically reactive. So they have a catalytic or adsorbing or whatever further chemical effect. The basic mechanical media would be sand or gravel. So that's the most basic medium. Or hydroanthracite, which is anthracite coal that is crushed and sieved to different grain sizes. This is used in multimedia filters, for example, also iron manganese removal. Then we have turbidex, which is a zeolite material that's mined, I think, from in certain places. And this has a better filtration effect than just sand filtration or multimedia filtration. So it removes particles up to smaller grain sizes.
So, and we have also these other materials which have a chemical reaction in the process they are used for. So first we start with activated carbon. So it's a catalytic surface, more or less, to remove the chlorine and organic material from the raw waters. So it's more or less a catalytic effect for the chlorine to be destroyed, and make no destroying effects in the membrane systems we have in mind, because afterwards comes a reverse osmosis with polyamide layers on the membranes which are damaged by these chlorine effects. So next is berm we want to talk about, and this is a material which is aluminium silicate coated with manganese dioxide, especially used for removal of iron and manganese. And because this manganese dioxide surface is a catalytic reaction, or enhances a catalytic reaction for the demanganization or de-ironing process. The Phylox is also one material which is quite new on the market, and I see that this filter media contains more or less 75 to 85% of manganese dioxide. Also this catalysator. In comparison, the berm contains a lot less of this mangan dioxide. It's only coated by mangan dioxide. And it's also used for removal of iron and manganese. I think if it's manganese dominated problem, in comparison to the iron, then we use normally Phyllox.
Right, I think we actually have one example project later where we use that. Okay, so the filter series, what we have, these are the basic simple filters, let's say. So HSF, which is a sand filter, HEF, which is a filter for removal of iron and manganese, and HAF, which is an activated carbon filter. These we use, let's say, more in drinking water applications, right? And we have tried to give you an indication of the boundary conditions. So let's say if you have drinking water and you have low solids, this is very approximately this 5 milligram per liter. So don't say it's 4.9, you need this, and it's 5.1, you need an MFT.
No, that's not how the world is. The world is not white and black. So.
Exactly. But we wanted to give you an indication to have a guideline.
Yeah.
So if you have relatively low iron concentrations, because our drinking water limit is 0.2, so if you're just slightly above, if you have some free chlorine but not a huge amount, then this is the best option. It's a very simple one, easy to install, easy to operate. You see here the flow rates, so they all go up to about 4 cubic meters. You can see also here that the sand and the activated carbon filter we use for the design 20 meters per hour filter velocity, and for the iron removal filter, it's lower. Keep that in mind because we'll explain later why that is so.
Yeah.
Okay, now for the big systems.
Okay, for the bigger systems, we have these MFTs. So it's only the diameter is bigger, and the filter valve is a Ciata valve, which allows more flow than 4 or 5 cubics per hour. So we are here in the dimension of the biggest MFT filter of 20 cubics per hour. So for the pretreatment of well water, surface water, process water, the boundary conditions, we say, okay, approximately TSS of less than 50 milligrams per liter, but that's a very high value.
That's already high. What happens when it gets really high, the TSS?
Yeah, so I think if you only calculate, just an example, you have 50 milligrams per liter TSS and you have 20 cubics per hour, then you filter out 1 kilogram per hour.
Sounds
1
like quite
kilogram dirt per hour. So let this filter operate 24 hours, then you have 24 kilograms of dirt on your gravel. And I think it needs to be backwashed then very often. So it needs to be backwashed because otherwise you have so much dirt in your system that you can go out anymore.
You would get a breakthrough anyway, or
pressure increase, and that's the reason why then the system has to be backwashed very regularly, very often.
Yeah, exactly. And when you have very, very short times for the filter run, in the end you use a lot more water for the backwash. You use at some point it's the same water that you put in, right?
Yeah, but sometimes you have no alternative. You have only this well water, or you have only this kind of water. You don't have city water, tap water in your region, and then you have to live with this. But then you have to build up strategies which enable that. So you have multimedia filters from small size to bigger size. We have there the opportunity to use different filter media, as we discussed already, Phyllox or Turbidex, or what is the aim of the filtering. And then we have possibilities. Also with controls, we have always the possibility to use S7, so PLCs or something like that. But the other thing we have also in our product portfolio is a sand filter for cooling circuits. And there it's a completely different aim. So we want to have less dirt in the cooling tower system than before. It's only a bleed off particle size bleed off system for cooling towers.
Oh, okay. And I think that's why it runs with higher filtration velocities.
Absolutely. Too. Yes. It's not really important if there is a breakthrough. If there is a breakthrough, then it has to be backwashed. And the backwash is normally also partly a bleed off you need anyway for the cooling circuit.
Right.
And that's why these sand filter for cooling circuits are very interesting for our clients. You can have also there different filter media, gravel as a gravel or as an AFM, glass granulate, and this has a special function of of germ reducing in these cooling towers, because cooling towers always have a problem and struggling with biological impacts.
Biofilm, all that.
Biofilms, exactly.
Okay. All right. So just one final word to remember, when you have more, let's say, complicated applications, and you want an MFT filter, you're not sure about the concentrations, it's always good to discuss with our application team
Exactly,
the
yes.
dimensioning.
Yeah.
Okay, some general words on dimensioning. And I think we have to hurry up. It's also interesting. So
it's me, sorry. I'm blocking everything. Okay.
But I think that's very good. It's important to get the details. Yeah. So generally, dimensioning is relatively easy, let's say. In the end, it's always you need a certain filter area, and you get that by dividing the flow rate. So you're, let's say, 10 cubic meters per hour by the filter velocity. Okay. Typical filter velocity for drinking water, for example, would be with a sand filter would be 10 to 20 meters per hour. Actually, drinking water, relatively clean water, is on the 20 meters per hour side. Yeah. Typical filter bed heights, that's also what we have, sort of. It's between 1.5 to 2.5 meters. Okay, 2.5 would be already very large. Those would be customized filters for us too, actually.
Because you will not be able to transport that only lying, but okay, I think our biggest filters, our MFT5 filters, are less than 2.5 meters.
Exactly. I think they have actually maybe 1.5 or 1 point something.
If you need a greater bed height, then you have to add filters in series.
We'll have an example about that too.
Exactly.
Okay, so basically the choice of the filter velocity depends on your type of water and on the degree of contamination, as well as on the filter media. We have some typical velocities for you. In the end, it has to be adapted in every project. So for sand filters, 10 to 20 meters per hour. You see that ours are designed for 20 for drinking water. If you have flocculation beforehand, you have to go slower because you have flocks already. So that's more like 7 to 10. And for iron manganese removal, it depends a lot on the chemistry. We'll see that in the next chapter. Yeah. So there it's very, very approximately between 5 and 15 meters per hour. You have seen for our HEF filters that it's given as 12.
Exactly.
When you do the backwash, of course, you have to be faster because you want to take out all the dirt that has accumulated on the filter. So typical velocities for us would be 30, 35, 40 meters per hour. Could also be more, depending on the material.
Depending on the material, yeah. Normally in the specifications of the material, there is a very good overview how is the backwash velocity there.
Exactly.
Good. Okay, let's go to the more difficult part of this presentation. So iron manganese removal. When do we need that? What is the oxidation process? Because it's not only a filtering process, it's a chemical reaction and then a filtering process. The components of the iron removal, basics of dimensioning, we have to present that, and the dimensioning of these iron removals.
Okay, so let's start right away. As you've seen before, for drinking water, it's usually not a problem. So the limit values in drinking water correspond to the limit values we give for the reverse osmosis. Yeah. And when the water supplier has done iron and manganese removal, the values are actually usually a lot lower than that. So usually we don't need that. It could be an option to use an HEF filter if you think the quality is so but doubtful, but that's more a police filter.
Yeah. But normally these iron and manganese removal systems are done in well waters, because in well waters very often the iron and manganese removal is required because sometimes they are very high concentrated, and we have to check. Normally you have to check or we have to check when it's critical, what measures, what we have to do against it. So we have to also to ask you to pay attention to the oxidation level of the iron and manganese, because if iron is already oxidized from the normal form to the oxidized form, then it's filterable. But if not, and if not enough oxygen is in the water, then we have a problem. Then we have to add oxygen.
And if you think about the filter velocities, right?
Yeah.
If you have a filter with 20 meters per hour compared to a filter with, let's say, 10 or 12 meters per hour, if you have to oxidize it, that would mean you have double the size of filter actually. So practically 50-60% more investment easily.
And you have surface water, which is normally not really have high levels of iron and manganese because, as I told you before, the oxidation, or the oxygen is available in a lake or in a river. And so the iron and manganese form is normally the oxidized form, and then it goes to the ground of the sea or in the river, and it's not in the water which you want to have in your RO feed. Okay,
so usually well water topic. Now we'll come to the oxidation process. So what happens here? The oxidation process is we oxidize iron 2 to iron 3, and the same goes for manganese 2 to, I think, 4.
Yeah.
What is important here, that's a relatively slow process compared to filtration. It's strongly pH dependent. That's why we always ask for the pH value and the alkalinity. Usually it's a bit easier for iron. The oxidation is a bit faster and it still occurs at a lower pH where manganese already has a problem. The reaction is affected by catalysis. You remember when we talked about the filter media, they are catalytic. So you get oxidized iron and manganese layers. I think that's actually a lot more important for manganese.
Manganese, really. It's dominant in manganese process that you have this manganese dioxide over the surface of this material. And normally you can use a material where the manganese dioxide is already impregnated, or you can wait because the manganese dioxide is formed during the process. You use a normal sand, a filter sand, and then demanganize. And the manganese goes on top of this sand and forms this manganese dioxide.
And you can add this KMnO4, a chemical to
improve
this process.
To improve this process, yeah.
Exactly. So that would also work. Then you have to dose it for the first few weeks.
Exactly,
maybe
yes.
1-2 months. And
then you have this layer, and then the system is running. But in the first few, I would say, weeks, first 4 weeks, there is no demanganization, no manganese removal. And after 4 weeks, we have this layer on the sand, and then the manganese removal starts.
So that would be the big advantage to use, let's say, Phylox or Worm
to
have this right away.
Immediately, yeah.
Okay. Good. We also have biological processes in iron and manganese removal. That's a bit complicated. Biology always is. But what is interesting, usually it's not recommended to use chlorine as oxidation agent. Usually you would use air.
Yeah.
Because you don't want to damage the microbiology in case they contribute to the oxidation process. What is important to consider here is if you have a water with a low alkalinity or low acid capacity, that means the pH would drop during oxidation because you always get H+ production, so the pH drops anyway. If you have a low alkalinity, it drops quicker, and at a pH lower than 6.2, you don't have any reaction anymore. It's just too slow. So that's why we always ask in the water analysis for the alkalinity and why it's really, really important. We'll see that in a sec for the dimensioning. Also, you need to take into account that other water constituents are oxidized. So if you put in air, you cannot choose what gets oxidized. Right?
If you have consumers which are consuming the oxygen before it goes to the demanganization process, then oxygen is spent already by the other constituents.
So if you have ammonia, for example, CH4 and H2S wouldn't be so common, but if you have ammonia, you would have to take that into account.
Yeah. Okay, the components for the iron manganese removal, we have an oxidator normally for bringing air into the system, to bring oxygen into the system. It's commonly used by an air injection point to oxidize the reduced iron and manganese compounds. So for very small plants, you can use a compressed air network in the site, or in bigger systems, you have to use a compressor for this air introduction. So also, as we told you, consider other constituents to calculate air demand. Filtration stage is the MFT filter and filter over the media for the removal of the oxidized particles, because before they are not oxidized, you cannot filter them out because they are perfectly dissolved. So we have a correct dimensioning of this filter. Velocity and bed height is very important. So generally, mangan is oxidized more slowly than iron. It's the more complicated process. It's the more sophisticated process, which needs a really adjusted pH value and something like that. High pH is always good for demanganization. A dosing of calcium permanganate is advantageous, as we talked before.
Okay, so now we come to the dimensioning, the interesting part. There are a lot of different approaches really for dimensioning. There are different calculations, there are different models out on the market. We want to show you this one that we work with as well. This is from the German Organization for Technical Rules, DVGW, DVGW. And they have a worksheet about iron and manganese filtration. And you see this approach here. You start out basically where you see the number 1, that's the iron concentration in milligram per liter. Mm-hmm. So you see here, this is for the lower concentrations between 0.5 to 1.5. Mm-hmm. And in this case, for example, this calculation, you start from 1.1 milligram per liter. You go up to look at the acid capacity, and this is where it gets important. It gets interesting. You see for the lower capacity, you will go to the left almost immediately. Yeah. With the higher acid capacity, you go up and then to the left.
So it's the alkalinity, I think.
Exactly, the alkalinity.
Alkalinity, yeah.
Has different names always. Yeah. Then you see the pH value at the filter inlet.
And they're also very important. If it's higher, then you go more to the left and to the better condition afterwards.
Exactly. So if it's under 6.8, well, you have a problem.
Nothing happens anymore.
Exactly. Yeah. So, and then the grain size of the filter material also has a certain impact. That's the number 4 here. So you go down and you choose which grain size more or less corresponds to yours, but it's not such a big influence. And then you go 5 to the filter bed height. So you can see here 1 meter, 1.5, 2 meters. And from there, you can go back and find your filter velocity. That's the number 6 in meters per hour. You see already here, the filter velocity, the area where we are moving is between 5 and 15 meters per hour. That's what we showed you before. And you see, we have the strong influence of the acid capacity or alkalinity. I think we have now an example of an actual project.
There we go, exactly the same way. So we have a well water with 0.7 milligrams per liter iron and 0.14 milligrams per liter manganese. And you see it's not so far away from the critical values. 0.2 is iron and 0.05 is manganese. But if we go through this chart here, then we get the resulting filter velocity of 11.5 meter per hour. So for the iron removal. And we have then to calculate the filter we have available. So the biggest one is the MFT5. At 20 meters per hour layout, it would bring 21.3 cubics per hour. At 11.5 meters per hour, which we calculated through the diagram, we have 12.5 cubics per hour through an MFT5. If we want to filter out 25 cubics per hour, then we have to use 2 of these MFT5.
Exactly. So it's important for dimensioning to remember you need to adjust the filter velocity. Don't just take for iron manganese removal the MFT as it is. No. And you can always calculate with so we don't give the area of the filter in the in our catalog, but you can easily calculate it because you have the flow rate, 21.3 cubic meters at 20 meters per hour. So you just divide that, you get the area, and then you can calculate actually what you need. So that's what we have done here as well.
So
good. We have to speed up a bit. Okay. So this is just will show very shortly, really, because this is something that our application team does. But to show you what is important, we have done here the design for iron removal. But in this case, we needed also manganese. So we have another tool where we calculate really also the time that manganese needs. And you can see here, you have the length of the filter bed, that's our x-axis, and you have the concentration in milligram per liter of the constituents. You see the iron is the red one, so that drops relatively quickly. After 0.7 meters already, it's down. Manganese is lower in the beginning, of course. It's the the black one. But it drops also a lot slower. So you need a second filter actually for the manganese and the ammonia removal. We have here ammonia as well. And you can see here, we need a total filter bed depth of more than 1.2 meters, which means we need 2 MFT filters, because one is approximately 1 meter, 1.1 meter. And that means in this case, we have to have a 2-stage process. The first filter is mainly iron. The second is more or less manganese. So that's a common case, I think, that we see very often. Good. So we'll start right away. When do you need it?
So I think drinking water is normally always necessary to have a softener, because the reverse osmosis, you remember this one, because you have there in this really narrow channels the problem not only that in the feed water is something which could precipitate in these small paths. You have also a concentrating process in the RO, and that's the problem. You have 4 times, 5 times, sometimes 10 times the concentration of initial feed water, and that's why this hardness is a really hard problem. In drinking water, in well water, sometimes in surface water, but not really existent. So I think drinking water is necessary to have this softening process. In well water, mostly also. In surface water, it's more or less coming from the rainwater. It's not really a big hardness problem there.
Okay. Then this is the ion exchange process. So that's the process we use in all our softeners. If we have a look at this, basically we have the hard water with magnesium, calcium going into the softener. We have the resin in there, the resin beads that you see in black. And the resin beads have active sites where they bind, or functional groups they're also called, where they bind calcium and magnesium, and they release sodium ions in return. So you get the resin beads, which are loaded with the calcium and magnesium, and you get the softened water, where the calcium and magnesium has been replaced by sodium. When you see that the resin fills up pretty much, so you see the increasing exhaustion here. First, the resin is yellow, that's the new resin, let's say. Then it gets depleted, and at some point you have a breakthrough and there's no free resin left. And then you need to regenerate your softener.
Before this happens, please.
Actually, before this happens. But well, usually you have some sort of limitron or behind the softener, so you will get an alarm when the softener is exhausted.
But normally you have safety times. After that, the system has to be regenerated without having the chance of breakthrough.
Exactly. So, and anyway, most of the applications, you set it for a certain cubic meters or timing, except for our Sensotrol, which is a bit more adaptable.
Okay, dimensioning. In Germany, we have some expressions about German hardness. Here you can calculate yourself from your commonly used expressions, ppm, calcium carbonate, to the degrees German hardness. The typical resin has 1.5 equivalents per liter as a concentration or as a measure of loading capacity of a resin. That's more or less the same as 4 degrees German hardness multiplied by cubic meters. That's the capacity of the resin. 1 liter of resin is equivalent to a capacity of 4 degrees German hardness by cubic meters.
And that's why you can always divide our, let's say, the softener capacity by 4 and get the liters of resin, right?
Exactly. That's it. And it makes a bit the dimensioning clearer, what we are doing and how the names of the Herco softeners are given, because the Herco softener has always a name of maybe Duodrol 2900, and the figure 2900 is the capacity in cubic meters by degrees German hardness. And divided by 4, then you come to the liters of resin in one exchanger.
Exactly. And if you know that the water has, let's say, 10 degrees German hardness, you would know that 2,900 unit can do 290 cubic meters.
Exactly. And that's the measure of your water meter, which has to be installed and adjusted. The hydraulic consideration is also very important because you don't have to float with a too high velocity over the resin. And we say 40 bed volumes per hour is okay. So that means also sometimes a minimal throughput is very, very important because if you have to slow velocities through a resin, the water can form paths through the resin without touching the resin and without to be then softened during the time running through the resin. That's why a minimum flow is also required. The time for the regeneration, or the time between 2 regenerations of one resin bed, is 7 hours because we are using brine tanks where the brine is made from salt tablets, and the time which is needed for dissolving the maximum brine concentration plus the time used for the regeneration itself is around 7 hours.
Right. Okay. Oh yes, but you can shorten that.
Oh yes, you have a trick, a cheap trick, I would say, and you can use 2 of those brine generators for reducing this time between 2 regenerations from 7 to 3.5 hours.
Like our Ecotrol P, for example.
For example, yes.
Okay, I think we'll just go quickly with these because we're relatively late. These are the softeners that we have. You see there are different types, different valves also, and different sizes. But since you know the systems pretty well, we'll skip that a bit. And we'll come to the examples. You see here again the different types, Ecotrol D and P, which is not shown, which has 2 tanks, as we said. And just only a very, very quick word. Normally, you would always design for certain cubic meters of water to pass or a certain time. But if you have different water sources, for example, and you have different hardnesses in your feed water, it could be a good option to go for the Sensotrol because it measures really the
breakthrough. It measures the breakthrough. It measures the chance or the possibility that the breakthrough can come. And that's measured by a sensor inside of the resin and tells you the right way to regenerate this softener.
Exactly. And the advantage is, of course, you know exactly when to regenerate when the resin is bent.
Exactly.
So you can save a lot of salt because you don't need to put in safety measures. Okay, but we'll go right away to the calculation, which I have some examples for the dimensioning.
Yes. The dimensioning, I told you already about the 7 hours between the 2 regenerations of a vessel. So the running time should be 7 hours. We have 2 examples, one extreme high in hardness, one extreme low in hardness. So city water in Würzburg. A softener of 10 cubics per hour has to be dimensioned for this water with a hardness of 38.6 degrees German hardness. That means around 650 ppm calcium carbonate. It's a very hard water. Calculation would be 38.6 by 10 by 7. And we have 2,702 cubic meters by degrees German hardness. So the next bigger Sensotrol system you can see on this table would be the size 2,900. You can make this cheap trick. You have a second brine tank with a brine valve inside, which feeds these 2 controllers on this Sensotrol, and then you have a size which is half the capacity, size 1,400. The other example shows you one speciality, because if the water has a very low hardness, as we have here in Freiberg in our site, with a hardness of 8.6 degrees German hardness, we have the same calculations, which would lead to 602. If you are a safety guy, you take the next bigger Sensortrol 800 to be sized then, and you have 800 cubic meters per degrees German hardness, which would be enough from the capacity, but the hydraulics should be also take into consideration, and this leads you then to a bigger sized softener, because the 40 bed volumes would not be enough for this 10 cubics per hour you want to soften.
And you see that here actually in the price list, the hydraulic capacity. So we would be from 1 to 8 cubic meters with a size 800 system, and we're actually at 10, so we're above. So the 1000 would be the correct one.
Exactly.
Okay, perfect. Okay, that was already the end of the softening part, and now we have for the last few minutes 3 interesting projects, which are not maybe the usual ones, just something that you see all the stuff that we have done.
So one example is that we've done a project in Vietnam for an OEM company in Germany who makes painting
lines, right? The whole paint shop.
The paint shop for automotive industries and for other industries. And they planned in Vietnam a big new project, and the water was very ugly there. So because it was high in TSS, not in iron and not in manganese, but only in TSS. And we thought how to overcome that problem. And the whole project you see here on the picture with a large RO. The RO was 25,000 liters per hour. So we need a pretreatment of around 35,000 liters per hour. And then we made a pretreatment as a filtering system, I think, with a PLC.
And I think single valve control.
And single valve control, yes. Very nice project. And we sent also somebody of our team to commission the system, or to help in commissioning, because it was only one guy.
Exactly, but I think he liked it.
Yeah, he liked it very much. I think he is very, very good travels there.
Yeah, interesting project.
Yeah.
Nice. And here is also the example that we mentioned before about iron and manganese removal. Yes. So this is a relatively recent project. This is treatment for well water, and that was for a food and beverage client in Germany.
Even better, it was a brewery.
Actually, yes. Pity we weren't on site, right?
No. Yeah.
But this is also with a PLC, and here it's interesting. You see we have an oxidator. We have an MFD5 for iron removal. And as we showed you before, it was also necessary here to have 2 filters, one after the other. And the second one is for manganese with this Phylox media, right?
Exactly. And we had an intermediate dosing of calcium permanganate, even though,
safety.
Because, yes, only safety. Because it's better to have more than to have less. You can switch it off if you don't need it.
Well, yes, that's true. That's true, but you always have the option.
Yeah, exactly.
And here you see how important it is to have this oxidized and the dissolved in total. So you had here with iron dissolved, it was 0.1 milligram per liter, but the total was actually 14. Imagine. Only that was actually all filterable. It was already oxidized, so it was easier. But manganese was the other way around. So that dissolved was the largest part. And I see we have a question also. Yes, we supply. So did we supply the systems as installed in the container? Exactly. So this is the container when it was here on site. We installed everything. We delivered, I think, the container, or did it come from the client? I think it came from us.
I don't know exactly.
But we do both options.
Yeah, we do both, yeah.
But we supplied it as a complete system, so only connection on site, and that's it. And now bear with us. It's 11, but we have only one example left. That is quite some time ago, but I think you probably remember that project.
Yeah. I remember that it was for a chemical industry in Russia, and the feed water was city water, pre-treated for RO with a PLC, And we had a softener, quite large softener towards 2000. We learned 2000 means divided by 4, 500 liters resin each softener with liquid brine supply. So we don't have to wait these 7 hours, because if we have liquid brine, we can do it quicker. And we had pre-treatment for 10 cubics of the reverse osmosis unit. The complicated thing on this was not the softener itself, it was more the documentation, because it was very, very complicated to make the documentation of this chemical industry plant in Russia. So this was the main topic for us.
Yeah, for these projects, it's a lot of documentation.
It was
lots
a very,
of folders,
very easy water treatment, but a very complicated documentation.
Yeah, that can also be a problem sometimes.
Oh yes.